My name is Santosh and I am a student of BSc Chemistry on our first year. Here is an audio video lecture on thermochemistry. Introduction. Many physical processes and chemical reactions are accompanied by the evolution or absorption of heat. Thermochemistry deals with the conversion of chemical energy into the heat energy and vice versa. Thermochemistry is the branch of chemistry which deals with the heat changes involved in a chemical reaction. The chemical reaction which proceed with the evolution of heat energy is called the exothermic reactions. In the exothermic reactions, the heat energy is transferred from system to surroundings, and the heat energy produced during the reaction is indicated by writing minus Q. The chemical reactions which proceed with the absorption of heat energy are called the endothermic reactions. In these reactions, the heat absorbed during the reaction is represented by writing plus Q. The heat absorbed or the evolved is expressed in the units of joule or kilojoules. Thermochemistry is based on the first law of thermodynamics. The energy changes that occur in the chemical reaction are largely due to the breaking of the bonds in the reactants and formation of new bonds in the products. Therefore, thermochemistry provides information regarding bond energy and the bond dissociation energy. The heat change involved in a chemical reaction depends on the condition under which the reaction is carried out. When the reaction is carried out at a constant volume, at heat change is related to the internal energy change. For a reaction taking place at the constant volume, W is 0. Hence, from first law of thermodynamics, delta U is equals to Q plus W, and delta U is equals to QV, where QV is heat change at the constant volume. If U reactant is the internal energy of the reactants and U products is the internal energy of the products, then delta U is equals to U product minus U reactant. And we may write delta U is equals to U product minus U reactant is equals to QV, that is heat of reaction at constant volume. Most of the reactions in the laboratory are performed at constant pressure, and the heat change QP is equals to the enthalpy change delta H. Delta H is equals to QP. If H reactants is the enthalpy of reactants and HP is enthalpy of products, then delta H is equals to sum of enthalpy of product minus sum of enthalpy of reactants. In an exothermic reaction, the summation of delta H reactants is greater than delta H summation of delta H products. As a result, there is evolution of heat and summation of delta H products will be greater than delta H reactants. Therefore, these reactions are accompanied by absorption of heat and delta H, and for endothermic reaction is positive. Standard state. The molar enthalpy of a reaction depends on the temperature and pressure. Therefore, for the sake of comparison, the values of delta H for different reactions are expressed at their standard state conditions. The standard state of a substance is its most stable state at 1 atmosphere pressure and a temperature of 298.15 Kelvin. The enthalpy of change at the standard state condition is called the standard enthalpy of the reaction. In other words, the standard enthalpy change of a reaction is the enthalpy change when all the reactants and the products are in their standard state. It is denoted by delta RH. The standard state condition refers to a 1 atmosphere pressure as 298.15 Kelvin temperature, and it is not possible to determine the absolute value of mole enthalpy of a substance. Therefore, to calculate the standard molar enthalpy of a substance, following convention is used. The molar enthalpy of every element in its standard state, that is 1 atmosphere pressure and 298.15 Kelvin temperature, in its most stable state is taken as 0. For example, at standard state, the most stable form of hydrogen, oxygen, mercury, bromine are H2 gas, O2 gas, Ag liquid, Br2 liquid, and I2 solid, respectively. In case of elements existing in two or more allotropic forms, the zero value is assigned the form which is most stable at 1 atmosphere pressure and 298.15 Kelvin. For example, for carbon, the standard molar enthalpy of carbon graphite is 0, but for carbon diamond is not 0. Similarly, for the allotropes of sulfur, the standard molar enthalpy for sulfur rhombic is 0, but for sulfur monoclinic is not equals to 0. Based on this convention, we can calculate standard molar enthalpy of any compound. For example, consider the formation of carbon dioxide from its element. Carbon graphite plus oxygen give rise to carbon dioxide. The standard enthalpy of reaction is given as delta RH is equals to summation of H product minus summation of H reactants, where H degree represent where H standard represent the standard molar enthalpy since the reactants carbon graphite and oxygen gas are in their standard states. Therefore, by the convention, their standard molar enthalpies are carbon standard H standard carbon graphite is equals to H standard oxygen gas is equals to their 0. Therefore, expression becomes delta R H standard is equals to H standard carbon dioxide minus 0 plus 0 is equals to H standard carbon dioxide. Thus, the standard molar enthalpy of a compound is the standard enthalpy of formation of the compound and is represented as delta FH degree. And in other words, the standard molar enthalpy of compound is equals to its standard enthalpy of formation. That is, H standard is equals to delta FH standard. Standard enthalpy of formation. The standard enthalpy of formation of a compound may be defined as the enthalpy change accompanying the formation of 1 mole of the compound from its constituent elements, all the substances being in their standard state. It is represented by delta F H standard. For example, for the formation of 1 mole of SO2 in a standard state from its element, we have sulfur solid plus oxygen gas give rise to sulfur dioxide gas. The standard enthalpy of formation of CH4 gas from its elements at 298 Kelvin is minus 74.81 kJ per mole. Carbon graphite plus H2 gas give rise to CH4 gas. Similar, the standard enthalpy of formation of HI gas from its elements in the standard state is minus 53.96 kJ per mole. Significance of the standard enthalpy of formation. Knowing the standard enthalpy of formation of reactants and the products, we can calculate the standard enthalpy change of any reaction. Standard enthalpy change of a reaction is equals to the difference of the standard enthalpy of products and the standard enthalpy of reactants. Standard enthalpy of combustion. It is the enthalpy change when 1 mole of the compound under standard condition is completely burned with requisite amount of the oxygen to form products in the standard states, and it is denoted by delta C H standard. For example, 1 mole of carbon graphite is completely burned. The reaction will be carbon graphite plus oxygen gas give rise to CO2 gas. The delta H standard will be equals to minus 393.5 kilojoule per mole. The standard enthalpy of combustion of graphite is minus 393.5 kJ per mole. Combustion reactions are always accompanied by evolution of heat. Therefore, delta C H standard is always negative. The enthalpy of combustion are measured by burning the compound in a closed steel container called the bomb calorimeter. During combustion, the temperature rises much above 298.15 Kelvin and pressure may also rise above 1 atmosphere. The standard enthalpy of combustion involves the total enthalpy change taking place with the starting reactants in their standard state and the final products also in their standard state. Enthalpy of neutralization. The enthalpy of neutralization is defined as the enthalpy change accompanying the complete neutralization of 1 gram equivalent an acid by 1 gram equivalent a base or vice versa in dilute aqueous solution. For example, when 1 gram equivalent of HCl is neutralized by NaOH, both in their dilute aqueous solution, the amount of heat evolved in is 57.32 kilojoule per mole. The neutralization reaction will be HCl aqueous plus NaOH aqueous give rise to NaCl aqueous plus H2O liquid. The delta H is equals to minus 57.32 kilojoule per mole. Thus, the enthalpy of neutralization of HCl with NaOH or vice versa is 57.32 kilojoule per mole. It is concluded from the data that the enthalpy of neutralization of strong acids with the strong base are almost the same. The average value of enthalpy of a strong acid by a strong base or vice versa is 57.32 kilojoule per mole. Thus, whenever a strong acid is neutralized with a strong base in a dilute solution, the enthalpy of neutralization is always equals to 57.32 kilojoule per mole. This can be easily explained by the help of theory of ionization. The strong acids and the strong bases are always completely ionized in their dilute solutions. If Ha represents a strong acid and BOH is the strong base, then the neutralization reaction can be written as H positive aqueous plus A negative aqueous plus B positive aqueous plus OH negative aqueous give rise to B positive aqueous plus A negative aqueous plus H2O liquid, and the delta H will be equals to minus 57.32 kilojoule per mole. Cancelling the common ions, the neutralization reactions become H positive aqueous plus OH negative aqueous give rise to H2O liquid, and the delta H will be equals to minus 57.32 kilojoule per mole. Thus, the enthalpy of neutralization is the enthalpy change when 1 mole of H positive aqueous ion in dilute solution are completely neutralized by OH negative ions to form 1 mole of undissociated water. Strong acids and the strong bases are completely ionized in the dilute aqueous solutions. Therefore, equal number of H positive aqueous ions and OH negative aqueous ions are produced by them in dilute aqueous solutions. Hence, the enthalpy of neutralization of a strong acid and strong base is minus 57.32 kilojoule per mole, irrespective of which strong acid or strong base is used. When weak acid or weak base is neutralized by strong base or strong acid respectively, the enthalpy of neutralization will be less than minus 57.32 kilojoule per mole. Consider the neutralization of weak acid like acetic acid with a strong base like NaOH. CH3COOH aqueous plus NaOH aqueous give rise to CH3CONa aqueous plus H2O liquid. Delta H will be equals to minus 55.23 kilojoule per mole. Acetic acid is a weak acid and is poorly ionized, whereas NaOH is a strong base and is completely ionized. In this case, the neutralization involves ionization of weak acid in addition to combination of H positive ions and OH negative ions. Therefore, a part of heat liberated during the combination of H positive ions and OH negative ions is utilized for the ionization of the acetic acid. The amount of heat used for the ionization of weak acid is called the enthalpy of ionization. The enthalpy of ionization of a weak acid is called the enthalpy of ionization. The enthalpy of ionization of acetic acid is plus 2.09 kilojoule per mole. Similarly, if the neutralization of a strong acid with a base is considered, the enthalpy of neutralization is again less than 57.32 kilojoule per mole. For example, the enthalpy of neutralization of a weak base, the ammonium hydroxide, strong acid HCl at 298 Kelvin is minus 51.34 kilojoule per mole. Therefore, some part of enthalpy of neutralization is used in the ionization of weak base NH4OH. Thus, the enthalpy of ionization of NH4OH is plus 5.98 kilojoule per mole. It may be noted that enthalpy of neutralization is the enthalpy change when 1 mole of H positive ions in the dilute solution are completely neutralized by the OH negative ions or vice versa to form the undissociated water. Enthalpy of neutralization is taken for 1 gram equivalent of acid with the base because 1 gram equivalent of an acid produces 1 mole of H positive ions on complete ionization. For example, 1 mole of H2SO4 produces 2 moles of H positive ions in aqueous solution, whereas 1 gram equivalent of H2SO4, that is 0.5 mole of H2SO4, gives 1 mole of H positive ions in dilute aqueous solution. Similarly, 1 gram equivalent of a weak base on complete ionization gives 1 mole of OH negative ions. The enthalpy of neutralization of a weak acid with a strong base or vice versa is always less than minus 57.32 kilojoule because some part of heat is utilized in the ionization of a weak acid or a weak base. The heat required to ionize a weak acid or weak base in aqueous solution is called the enthalpy of ionization. Hess law of constant heat summation. The energy changes accompanying chemical reactions are governed by the general principle known as the Hess law. This law states that the total amount of heat absorbed or evolved for a chemical reaction is same whether the reaction takes place in a single step or in a number of steps. In other words, the total amount of heat change in a reaction depends only upon the enthalpy of the reactants and the enthalpy of product, irrespective of path or the method of which change has taken place. For example, carbon can be burnt to carbon dioxide directly in a single step, and in this process the amount of heat energy is 393.5 kilojoule per mole. Other way is to convert the carbon to carbon monoxide, which is then oxidized to carbon dioxide. The net reaction will be carbon plus oxygen give rise to carbon dioxide. Delta H will be equals to minus 110.5 plus minus 283 e raised to minus 393.5 kilojoule per mole. Thus, ET hold is same, that is 3 minus 393.5 kilojoule per mole if carbon is burned to carbon dioxide in a single step or in two steps. Similarly, sulfur, that is monoclinic, burns directly to form sulfur dioxide in a single step. Sulfur monoclinic plus oxygen gas give rise to SO3, that is delta H is equals to minus 300 kilojoule per mole. This change can be brought about in two steps also. The reaction will be sulfur monoclinic plus 3 by 2 oxygen gas that gives rise to SO3. Here also the enthalpy of reaction will be minus 300 kilojoule per mole. So the enthalpy change is same whether the sulfur monoclinic is burnt in one step or in two steps. Proof of Hess law on thermodynamics basis. The thermodynamic basis of Hess law is that enthalpy is a state function. Therefore, the enthalpy change delta H depends only on the initial state and the final state of the system. Delta H is independent of the path by which the reaction is performed. Hess law is and in accordance with the law of conservation of energy. Application of Hess law. As a consequence of Hess law, the thermochemical equations can be added and subtracted just like algebraic equations. As a result, it is possible to calculate the enthalpy change for the reactions for which the direct measurement is not possible. And some of the important applications of Hess law are the following. First is to predicting the enthalpy change for any reaction. Hess law can be applied to calculate the enthalpy of any reaction whose direct measurement is different or even impossible. Second one is the determination of the enthalpy of transition. Some elements exist in allotropic forms. Hess law is useful in determining the enthalpy of transition of one allotropic form of a substance to another. The transition like graphite to diamond, red phosphorus to yellow phosphorus are very slow. The enthalpy change accompanying these transitions cannot be measured directly but can be determined using Hess law. And the third one is the determination of enthalpy of hydration. Direct measurement of enthalpy of hydration is not possible. However, use of Hess law makes it possible. Heat of reaction at constant volume and constant pressure. The heat change for a process carried out at a constant pressure is different from heat change at constant volume and temperature. The significance of delta U and delta H can be followed from the first law of thermodynamics. According to the first law, delta U is equals to Q plus W. Assuming that the volume delta V changes during the process of expansion against constant pressure P, the work done by the system will be W is equals to minus P delta V. Delta U is equals to Q minus P delta V. Q will be equals to delta U plus P delta V. When the process is carried out at a constant volume, delta V will be 0. So QV is equals to delta U. The heat absorbed or evolved at the constant volume and constant temperature is equal to the change in the internal energy. Enthalpy is defined as H is equal to U plus PV. Change in enthalpy delta H may be written as delta H is equal to delta U plus P delta V plus V delta P. If the process is carried out at a constant pressure, then delta P will be 0. So delta H will be equal to delta U plus P delta V. And substituting the value of delta U from the equation first into the equation third, we get delta H is equals to Q minus P delta V plus P delta V, that is equals to Q. So delta H will be equals to QP. So QP is equals to delta H. Heat of reaction at constant pressure is equals to the enthalpy change. Delta H and delta U are equal if the reaction involves only solid or liquids or solutions. However, when the reaction involves gases, the difference between delta H and delta U becomes significant. Consider a reaction at constant temperature T and pressure P. Let P1 be with the volume of the N1 moles of gases reactants and V2 is the total volume of N2 moles of gases product. For example, for ideal gas PV is equals to nRT, PV1 will be equals to N1RT, PV2 is equals to N2RT. PV2 minus V1 is equals to N2 minus N1 upon N2 minus N1 into RT. P delta V will be equals to delta NG RT. Delta Ng is the change in the number of gaseous moles of products and the reactants. Thus, the reaction can be written as delta H is equals to delta U plus delta NGRT. Substituting for the delta V and delta H from the above equation, we get QP is equals to QV plus delta NGRT. Conditions under which delta H is equals to delta U or QP is equals to QV. Reaction which do not involve any gaseous components like HCl aqueous plus NaOH aqueous give rise to NaCl aqueous plus H2 liquid. Reactions carried out in a closed vessel means delta V is equals to 0. Reactions which involves gaseous reactants and products, but the number of moles of reactants is equals to the number of moles of products means delta Ng is equals to 0. Thank you.